Yay, Jeff is here. You might want to do an audio check as well, Jeff.
Audio check. Can you hear me?
Yes.
Theoretically, this has video as well, although I don't see any video.
You have a nice pair of
I see your video either.
That's probably a good thing considering the time of the morning. In fact, I think I'm going to turn off video because you know I'm only going to be black no matter what.
Well, none of us have had a good haircut in a year, right? So, you know.
So, you know, you just don't
A
want
lot
to see
longer than a year. How long have we known each other?
A good point. I've never had a good haircut. That's my head's fault.
Well, maybe I should share a title slide. That would be exciting, wouldn't it?
It seems wise.
Yay.
So it looks like people are starting to join increasingly fast, quickly. So I guess we should give it a few minutes for everybody to sign in, figure out where all the buttons are, etc. Although I will note we do have a full agenda, so maybe not too long.
Well, you tell me when to start, Warren.
I'm not taking that kind of responsibility. I guess let's give it to about 3 or 4 minutes after the hour and start then. Yes, while we're waiting for people to join, I will just note that this is the second part in the technology deep dives in the DNS. The first part happened at IETF 108, and the video is online on YouTube, and I believe is also linked to from the IETF website somewhere. I realize that was not the most useful update ever, but if you look around, you should be able to find it. Otherwise, email me, or I will try and remember to put a update somewhere. I think the invite to this or agenda also has a link to last time's recording, and it's probably useful if you're not particularly familiar with the DNS to go and read that or watch that. And I will also note this kind of builds on that and also explains that a lot of what we told you last time, we were actually lying about.
I don't think the camera works. That's a scary photo.
just very bright sun.
Your camera is working now, Jeff.
My camera is working. But, you know, like I said, it's really dark out there, and, you know, I could go all shadowy.
It's working, but it's not working well because you're much more handsome in person.
Warren, you're just too kind.
I am. It's because usually I give you abuse. So figured seeing as we have
Okay.
lots of people watching, I should be polite for once.
Don't
Anyway,
worry
maybe
about
we
it.
should.
Time is of the essence. Look, welcome everybody. And for those in the Asia Pacific area, particularly those in Japan, I feel your pain. Here in the east coast of Australia, it is, a civilized 4 a.m. In parts further west from me, it's not. It's worse. For the next hour and a half, we're going to be talking DNS. It's when too much DNS is barely enough. And this is the second part of these deep dive sessions. So we're going to dive a little bit deeper and have a look at some of the underlying issues inside the DNS, looking at the concepts of names, which I will cover, and what they mean in the context of the DNS, looking at some of the sort of security issues that come up with the way in which we use names, which Wes is going to cover, and cover some of the more prevalent myths, fantasies, and misconceptions that that sit within the DNS, and see what else we can uncover. So we'll have 90 minutes, which is a comfortable amount of time. What I would like to do is sort of channel through pretty quickly, and then take a small number of questions and hand to Wes. But we have reserved around about 30 minutes at the end, possibly longer, to actually wander through your questions and our feeble attempts at trying to provide answers, or maybe you can provide the answers and we'll just provide the questions, which I personally prefer, because it's going to take about that long for my brain to boot up. And don't forget, I haven't had coffee yet. So with that said, let's start. The usual. Read this carefully, note it well. You have 2 seconds. Done. Let's start by thinking about what a name is. And wasn't it Shakespeare in Romeo and Juliet? What's in a name arose by any other something or other. My memory is now gone. A name, we use it as kind of a human-based token, an alias for what we would call an address. An address is something, an endpoint destination, that an IP network uses to relay a packet. And so all we're doing with a name in this kind of destination-based packet forwarding network is providing an alias for an IP address. Now, we're not talking about why you wanted to send a packet there. It's just the name of an IP address, the name of a host. In fact, to be perfectly frank, the name of an interface on a host. And it's up to something else, the transport protocol port address normally, to effectively select what the service is that you're trying to get to on that host. The name itself, well, I actually said the name of the platform, not the particular service, but to be brutally honest, that's not quite correct. It's the name of the IP address of the interface of the platform, not the name of the service. But in any case, it's not a service name. And the intention was, this is human use. This is about things that you and I use as people talking, a natural language. It wasn't an artifact of the network. When the packet, the IP packet, heads to its destination, the IP part of the packet, never mind transport and application, does not have any use of a name. All that you find there is those v432 bits, v6 128-bit source and destination IP addresses. There are no names there. We are not routing names in this architecture. So they were intended, at least, and I'm going back about 40 or 50 years, it was so much more useful if the same host had the same name, irrespective of the protocol. So if you're going to use UUCP or UUNet mail, that kind of issue, if you're going to use IP mail, if you're going to use any other form of protocol family, it's very useful if the name is constant. I'm going to go to the host called Fred, almost irrespective of what protocol I'm going to use. So to make that work, you actually had to have these host names specified as the lowest common denominator across all of these protocol-specific and application-specific limitations. And so host names took a much smaller character repertoire than actually is possible inside DNS labels, which Joao is going to explore in incredible detail later on. And just to illustrate this, I've actually jumped Joao's name into Unicode to sort of point out that even in our human use, what we think is a character repertoire varies language by language. So there's some very subtle distinctions going on here around the names of hosts and the names of labels. And the rules for hosts are, of course, much more constrained. And the answer is why? Well, it's nothing to do with the DNS per se. The DNS in that area, quite frankly, doesn't care and doesn't make that distinction in and of itself. It's more about mapping protocols and names into applications. So let's talk a little bit about the resource record. Now, the original naming model was based on a thing that we always came to call host.txt. It was a very, very simple entry. It was a text file with one mapping per name, per entry, and it had an IP address, a space, and then a set of names that were aliases for that IP address. And so when you said, what's the name of Jeff, you'd look down host.txt and find a name match, a line that had Jeff, and you'd find the corresponding IP address and send it back. There are one or more IP addresses listed in those entries. I'm not sure about the order. It's been so long since I've ever had to use host.txt. Most machines still have an echo, a ghost of that file, sitting somewhere inside the file system. And it's a common form of malware to go and make some evil entries there, because it normally takes precedence over the DNS. We probably should have got rid of it. Host.txt is client-centric. So you could have a host.txt that calls the IP address, 1234 Fred, and I could call it Jeff, and Joao could call it Bob, and no one would care. Because while we're referring to the different hosts with the same host with different names, the DNS doesn't, sorry, the host didn't care, and actually your applications didn't care. However, when we turned into a distributed database, all of a sudden the name became unique, because we're all sharing one database. We don't have different hosts.txt per se. We're all working in one database. But the database itself was distributed. It wasn't just, oh, host.txt exists on a server over there. There is going to melt. We distributed it. And so everyone ran a little bit of this database. But in a distributed database, you need mapping records to say, I don't know anything about this name. The person, the thing, the host that knows about this name is over there. And so I'm authoritative for a bundle of names, and all these other hosts are authoritative for other bundles of names. So we had added two more records into this distributed database. We had the name to IP address mapping, originally called an A record, A for address. We also had SOA record, start of authority. That was, if you will, all the names in this bundle that are related have the common set of properties. These are the properties: the zone administration, contact, expiry timers, time to live, and so on. If it's not specified, use this value. And the names that I don't know about, which are child names in a hierarchical system, well, you can find them over there, where there is a name server record, the name of the host serving those names. So we added two more resource records, SOA and NS. But how do you disambiguate services? Excuse me. Because you might want to have different services connected to the same host, and you might want to explicitly label them. So we started making that an attribute of the name itself. So rather than saying queryexample.com and get an address and attach to port 80 at the time, because we were banging the rocks together then, we actually said, no, you want to go to dub. And so now it's sort of belt and braces. It's an alias, the dub, for giving a name that you subsequently go to port 80 on. And so you can distinguish that from ftp.example.com and mx.example.com and blah, 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 where you're actually putting the service name on the left-hand side as part of the query name. So this allowed you to specify a set of hosts, different hosts, that supported the services that had a common name. And all of a sudden, you're creating this extra bundle of semantics about that name, because now www.example.com can be a separate machine providing a service in the name of this supposed host, example.com. And you can have a number of these things with different services, all mapping to different IP addresses, supporting a host service for the common name. So all of a sudden, I've got greater capacity, I've got service disambiguation. But why don't I make the DNS work harder? Well, obviously, why not? Because I can. So why don't I include the name in the protocol exchange itself? Hi, host. I've got a transaction for www.example.com, says the application. Now, the first one to do that was actually electronic mail, because one of the early needs was to provide mail when the host was down. So we had secondary MX servers that basically provided a mail service for a host that wasn't there. Because don't forget, in the days before Gmail, if anyone's still old enough to remember that, in the days before Gmail, a lot of us ran our own mail hosts, their own send mail, and maybe we were on dial-up. Remember that? And so all of a sudden, when you weren't there, you didn't want to back the mail up at the sender. You actually wanted to back the mail up at a relay host closer to you. And so adding MX records allowed you to create those relay hosts. And the issue was that when I connected to a machine that was my mail server, in the application itself, I would be able to say, I want to send mail to, and you specify the name of the server in the application. So service names actually started to migrate into application attributes. So they're abstractions, weren't they? They allowed orchestration of multiple servers. Now, some of these we loaded through the DNS itself. So the common service name, which is no longer a host name, then had a variety of attributes through different resource records, NS records, MX records, and such. But then we thought, well, actually, what I'd like to do is move the service for a host to a different name. And we invented the alias record, the canonical name record, or the CNAME record. Whereas most of these service names are implicit, the A and Quad A records, which give you IP addresses, simply says the service delivery host is mapped against this service name. So this allows us to sort of think about what a name is now. It started off by effectively taking the idea of the name of a host, a computer, the interface of that computer, and actually abstracting that to a universally visible service point identifier. It's the name of a service, not a host. But we've also used a whole bunch of other names. There are a whole set, probably outnumbering human names these days, of transient labels, dynamically generated names of various forms and sorts, where it's just a temporal name. Here's a token, here's a machine over there that for the next 10, 15 microseconds might well serve as a point of rendezvous with what you're trying to do. NS records, a name is a bridging point to glue together the DNS database. Or oddly enough, you can think of the name as a piece of microcode and think of both recursive and authoritative servers as microcode interpreters. And so the name directs the server to do certain things. Now, in theory, it's a database lookup key, and in theory, this is a database lookup. But quite frankly, using various DNS libraries even today, you can create dynamic labels that cause particular actions on the name of the server because it's microcode. It's just name is code. So a name is actually all of that and more, just to add to the confusion. And so how do we then do service identification? And I suppose the observation is that every time we've looked at this, and we've looked at this a lot of times, we propose a new generic mechanism that can be used with any application. Wonderful. But each time we invent this, one application uses that and we move on. So every application uses a unique, quite specific, but generic DNS solution as to how to do this. So when we map names to services, we can place the information in the value part of this key value store. And, you know, the service, the SVC record, is a classic example of trying to place rendezvous information in the right-hand side of the DNS, in the resolution side. Or we can play with the left-hand side, the query name, and we can use the DNS to go, you meant to go to foo.example.com, the service is at bar.example.com. In other words, map the service name through the left-hand side. Or we can modify the query type itself to have different application data. And actually, don't query for an A or a quad A record, query for one of these. So the first time we found one of these, I'm not sure what was in the head of the folk who designed it, but in the people who came subsequently, this was the Texas Chainsaw Massacre of text records, the universal thing, because text records is just that. It's text. It's ASCII strings. I can put anything there. I can hash anything there. I can stuff most things in there. And lots of people have seen this because the text record itself is just a string of data, a value. And if the application says, structure the value with saying, field 1 equals value 1, field 2 equals value 2, just put that in a text record, that's fine. The problem is, of course, that if everyone used text records, then, excuse me, you have to make text records which are the union of all these applications, and disambiguating which text record is meant for which application can be an enormous problem. But you know, if the thought is no matter what you want to do, you can do it in the DNS, then the next thought is no matter what you thought you wanted to do, use a text record because you know you can get away with it. Text records are just the universal garbage bin of the DNS, and for a good reason, they're completely unstructured. Now, there were some various attempts to do this, and the first time we sort of did this in a structured way, we thought we would actually give a name to a structure of a text record. And this was the sender policy framework for mail, and we call them SPF records. In truth, they're just text records with a particular structure. And you see this attempt to be to be specific in a generic solution. So the first part of this, you actually have the V equals SPF1, and then a bunch of fields and values. Interestingly, the recommended syntax is use an equal sign first, but then use colons, because, you know, consistency is great. What I also like in SPF to actually really make this incredibly evil is the include function, which basically says, go and include all this data. And what I didn't go is include example.com, because as soon as you actually start to do domain names in the value side of a resource record, as soon as you do that, you admit the potential to create loops inside resolution of names, inside finding a value. And the SPF was actually one of the first as well that not only used the text record in a structured way, but also used loops in a, well, used loops in a whatever way. Earlier than that, though, and as an example of doing it probably a little bit better, was the MX record, where here the information you want to give is actually structured by the name of the resource record. So instead of just querying for a text record, you actually query for a particular structured record, MX. And yes, there are names on the right-hand side, but the way they've disambiguated and stopped looping was that the names on the right-hand side are not MX records themselves. To query the value of example.org for an MX, you get back in this example, smtp.example.org. But what you don't do is query smtp.example.org for an MX. You're not trying to resolve that. You're trying to actually find its IP address. And so the MX record doesn't loop on MXs, which is probably a really, really, really good thing. And so here is an example where you're trying to say that if I'm going to send mail to example.org, I'm going to send it over to the name SMTP1, whereas if I'm going to send mail to, sorry, if I'm going to send mail to www.example.org, I'd go to SMTP. If I'm going to send mail to example.org, different name, I send mail elsewhere. And that's certainly possible in MX records. C names and D names, I always thought were bizarre. This is actually creating aliases in the resolution of names, not in the namespace itself. It's in the resolution. So you have two perfectly normal trees here in this example, which we borrowed from slide 37 of last time, if you were listening carefully. There'll be a test later. C names and D names are relatively similar, except that C names stop at that name and resume over there. So it's a canonical name for a terminal name. There is nothing below a C name, no matter what. So when you get to a C name record, that's it. Whereas in a D name, you resume name resolution at the point below the D name target. So the D name is aliases for, I said zones, or at least the slide last time said zones. No, it's actually aliases for the entire subtree. So anything below a D name on the left-hand side isn't reachable, nothing there. But on the left-hand side, on the right bit, sorry, below on the right-hand side, I'm still tired, the D name exposes the entire subtree. In a C name, that's it. Both on the left and the right-hand side, there is nothing. They exist alone. They can't be at the apex. There's nothing below it. They are terminal names. And I suppose that's the distinction between a C name and a D name. A D name is an alias higher up in the tree, or potentially so. A C name is an alias for terminal labels. There is nothing below them. Even so, names on the right-hand side are a problem. And certainly here are some simple examples to basically illustrate the fact that dog and cat can be C-named to each other. And the only way of stopping this is for the resolver to say, look, enough is enough. Stop giving me a hard time. Because while it might be easy to detect a loop of 2, it's incredibly challenging to detect a loop of 100, say. And there are two problems with these kinds of loops. The resolver might well make cache entries for every single entry and just keep on flicking over again and again and again. And of course, it takes an awfully long time for the poor old resolver to figure out that it's inside a loop. And so this is one case where the structure of the namespace itself can cause problems as soon as a triggering query exercises that looping structure. But, you know, we can do more. And it's hard to say whether the NAPTA was just fashionable or a demonic invention of incredible evilness, but it was certainly cute. What happens if we take a text value and throw it into a regular expression parser, and inside the DNS actually put that regular expression? And I've taken this example from the documentation, but let me assure you, these are regular expressions, and there is more than enough rope to do anything you want. The challenge is to do the Towers of Hanoi in NAPTA records. Go forth. It's hard to sort of talk about this in much detail, but what it's saying is, if you look up a NAPTA, you get a priority and you get effectively an application directive. And then you get this weird thing of you saying, take the application string you thought you were looking for and substitute the following. So here's one that was borrowed for that early attempt to burrow telephone numbers into the DNS, enum, which we thought at the time was incredibly clever. And the generic solution we had was take a reverse telephone number +71 705 551 212 and translate it using only the DNS into a SIP call to an alias called information from the server Tele2 in Sweden. Okay. I wonder if anyone used it. Maybe they did at the time. I think it's fallen largely into disuse. It really did get and push the DNS an awfully long way. So generically, what's going on? Well, you can put loops in the DNS in all kinds of places in all kinds of ways. You can actually put loops outside of the DNS database structure and put it in the name referencing structure. So in essence, what we're doing at this particular point is doing forwarder clauses. Hey, I can't do anything, go and speak to X. And X says, I can't do anything, here's a forwarder statement, go and speak to Y. And Y says, I can't do anything, go and speak to X. And all of a sudden, you have loops inside the forwarding chains of trying to resolve. But the more common form of loop is actually in the DNS data itself. And you can certainly do NS record loops quite easily. Normally, the parent zone contains the glue records of the name servers. But what if you don't? The name server for my domain is dog.com. Go figure. And in dog, it says, well, that's cool, but the name server for my name is cat, but I'm not going to tell you its address. And cat says, hey, the name server for my name is over in dog. All of a sudden, you've got loops inside the NS structure. And again, if not handled sensibly by the resolver, you can follow that loop forever. And so some ways resolvers have to make sure that they're not retracking over resolution tasks when they're trying to figure out the names of name servers. And equally, CNAMEs, DNAMEs, and NAPTers can loop like crazy because it's simple. Now we get on to the last part of this and actually look at now trying to make the DNS offload a whole bunch of application level data and simply load this into the DNS and make the DNS not an alias for a name, but a service rendezvous mechanism. So here, what you're trying to say is, I want to connect to SIP, the SIP port, using TCP of example.com. You're being quite specific about your intention. And in the service record, you can use leading underscores, which in host names is a no-no. Host names don't allow underscores, and certainly not leading underscores. So underscore SIP, underscore TCP, talks about a service record which is in particular meant to be used for the SIP port on a TCP connection to the named host. And here is the service that actually provides that service for example.com. Go and speak using that port and that protocol to someone else. And so it's a subtle form of alias where it's not the name that is aliased, the service is aliased. So I can take example.com and I can alias my SIP service to someone. In theory, I could alias my HTTP service to someone else. I could alias my DANE service to someone, and I could alias the name to a whole bunch of other names simply by service protocol and port, while having the common name simply, as you will, the guiding point. So the right-hand side host now is the canonical name, but unlike a CNAME or a DNAME, no matter what you're trying to do, look there. This is, if you're trying to use SIP on TCP, look there. If you're trying to do anything else, I don't know. I'm not the record to talk about everything else. So it's quite a specific record. But oddly enough, every generic solution is never generic enough. And when we looked at CNAMEs and we couldn't do an alias at the root, because the apex, sorry, because you can't alias at the apex, folk wanted to do that, but I want to do this. So we experimented around with various permutations of what I would call a name. And a name was an alias that included aliasing at the apex. There were alternatives for service records, alt servers. And then when we looked at encrypted SNR, we wanted to put the keys somewhere. And these are all attributes of a rendezvous, trying to get to somewhere. And so what if we try and make this generic and take all of these things and put it in a generic service form, which became service B. And service B looks a little bit like a structured text record again. Yay, come back SPF. Where now we've got two forms of a service record. This port, this protocol, this host has an alias form to somewhere else, just this port and this protocol, and somewhere else now has a whole bunch of attributes that talk about the application level protocol name, the port name, the keys name, the this name. So all of a sudden you can say that foo.apiexample.com and this port 8443 is alias to use an application level protocol called bar and service endpoints offered on this host using this port, etc. And so now, oddly enough, all of the work that you would do somewhere else at the application level in redirections and other forms, you can now do in the DNS, generic solution. And of course, it's only used in one particular context, so why not just go there? And this is service B for HTTPS, which is currently being standardized, or if it isn't already. And it's the equivalent of service B for the HTTPS scheme. And now you get the full appreciation of what's going on here. Because if in first use you find an HTTP header that had this record, that there's an alt service field in the data that says, well, you've come to me, but in future go to there. You can eliminate that completely by simply saying in the DNS, if you wanted to go there, you should go over here, and have a whole bunch of aliases. And so what we're doing now is actually making the DNS not just map host names to host addresses. We're now mapping your immediate intentions. I want to use HTTPS to go to this service name. This is my immediate intention, into the DNS telling you exactly what those service rendezvous mechanisms should be, what protocols to use, what ports to use, what attributes you're going to use at the application level in order to make that connection work. Why do we do this? Because it's faster. Because all of a sudden, I'm getting rid of that first look. I'm getting rid of redirection to the application level. By pushing stuff into the DNS, the theory goes, and it's not always true, that the DNS can give you that rendezvous information much, much faster. But in some ways, this is not the best of things. And this is my lead, I think, into where Wes is going to be. I've used more than enough time. I'm 4 minutes over. DNS is not secure. And anything that is promiscuous, and the DNS is promiscuous, no matter how we try, is not completely private. Some information is always going to have to be public, because this is public rendezvous. And to what extent, if now we're saying, I just want not just the IP address of a host, but I intend to connect to foundaffa.org or some other evil name. But more than that, I intend to use this protocol and this port. I intend to do the following. And the DNS goes, absolutely, here's how you do it. But there's a trade-off now, because now I'm telling a whole lot more to the DNS about what I'm about to do in the next microsecond. And maybe that's not a really good thing. So Wes is going to explain why that not be the best of ideas. Thank you.
All right, thank you, Jeff. Yes, so the DNS is not secure. The DNS was not secure would be the other way to possibly do it. Let me share my slides. And so I'm going to talk for the next half an hour about DNS security, and I'm Wes Hardiker from the Information Sciences Institute. And this is the 30-minute overview of DNS security. However, first I want to touch on something I did last time. So this is actually my wildcard slide from the DNS Deep Dive #1, and there's a mistake on it. And this was the last slide I created, and you know what happens when you create the very last thing always has the most mistakes, because it gets the least review. So it actually occurred with this top record down here, where I had said at the time that host1.example.com/mx matched the wildcard. It does not. It actually should not match, and it should return no error. But the text up above actually should have called this out as well. It matches any label that doesn't already exist. But that label did exist down here in the actual example records. So thanks very much to Andre for catching that and pointing it out to me. And so that's the errata. And then now we'll actually dive into DNS security. we're going to start by looking at sort of the attack surfaces. Where can DNS be attacked? And like, most other protocols that started in the internet, they weren't secure in the beginning because everybody believed that the network should be trusted. That's certainly no longer the case. I'm stealing a slide from Russ Mundy, who has talked about this at ICANN meetings and a number of other places, to talk about how the DNS actually is put together from a registration point of view. So maybe some zone content wants to start, and you have, hey, I have this great new domain, it's called IETF.org, and I need to register it somewhere. So you go through some registrar in order to actually attach it to the DNS tree, attach your specific section to the DNS tree. The IETF uses Network Solutions. And then it's hosted in a registry, like PAR happens to run .org. And that is actually how your particular name servers get linked into the whole tree. And in fact, the IETF.org uses ns0.amsl.com as one of their name servers. I'm only listing one. And resolvers can then query that. That includes ISPs and the quad public resolvers and Open DNS and some of the other resolvers. And then finally, the data gets all the way back down to DNS users and applications. The important thing to note that most of what I'm going to be talking about today is over on the right-hand side. I have one next slide on the registration area, but we're not going to touch that too much. We're going to talk a lot more about the right-hand side. The important thing to note, of course, is that evil people can do stuff to pretty much anywhere in the entire tree, so do be aware of that. So if we talk about the registration side, there are sources of insecurity all throughout the DNS, and the question you should ask is, what is the best way I could get data into the DNS itself, right? If you really want to populate the DNS tree with bad information, you should actually do it during the publication side. And there are well-known mechanisms for doing so, a lot of which include social engineering on the publication side, on both the registry and the registrar. And then you can also attack the zone itself. None of the security protocols I'm about to talk about help at all if you don't have your source of your data secured in the first place. So if somebody can take over where your data is coming from, then the DNS security mechanisms are not going to help you at all. On the publication and consumption side, there's a number of ways that things can be attacked. So we're going to talk about cache poisoning as sort of one of the oldest and not quite as relevant these days, but the DNS security mechanisms were trying to fix. We'll also talk about DDoS attacks and what happens there. Jeff already talked about loops, so I'm not going to go into them in my slides. And then we're going to talk about privacy, because queries can be seen by both resolvers and authoritative servers, as Jeff indicated sort of at the end of his talk. And then finally, we'll talk a little bit about DNS abuse and deception, and the interesting things are what happens when there's typos registered in the domains that aren't from the domain itself, or internationalization and other font-related issues. And Joao's going to talk about that after I'm done. So a little bit of architecture refresher. I'm sure most people remember this, that when some example.com is queried for a record, that the resolver near you, be it an ISP or be it in a nearby box or whatever, ends up needing to talk to most of the tree. It'll start by talking to the root, which then it finds .com, and then it finds example.com, and then finally that's able to return www. So what is cache poisoning? So remember that resolvers actually cache information for a period of time that is subject to the data itself, a maximum period of time. And what happens is your laptop may query the resolver, and the resolver is going to, maybe it has the root and com cached, and it's going to send its query immediately to www.example.com. Note that www.example.com or the example.com authoritative server is probably really far away. So if the resolver is getting an answer first from somebody really nearby that is giving it a false answer, then the resolver may believe that answer. So in this case, the resolver answers, but it's before the authoritative server could possibly have answered. And so the thing about DNS is that the first answer wins, period. So you may get multiple answers. The IETF has long talked about, you have to expect duplicate packets and stuff and duplicate answers, and you should pick the first. Well, that works if that works really well for attackers if you aren't able to check the data. So one of the earliest cache poisoning attacks, the things that actually made cache poisoning possible, was just to include extra data in the additional section. So at the end of the DNS packet, not only does it give you information about the question you asked about at the top, but at the bottom in the additional section, there's also other records. And early resolvers would actually just trust anything that was there. So you could include records that were totally unrelated to the question, and the resolver would cache it and keep it. The other thing that happens is in protocol attacks, you can actually sometimes just flood the DNS resolver with response packets and hope that they accept them. If you're actually, on the wire, if you're a man in the middle attack or a person in the middle attack, then you can actually possibly see the values. Otherwise, you end up having to guess, the IP address, the protocol values, the names, the source addresses, and things like that. Maybe you can see some of them. You can pick popular names to try and flood the most. And actually, that was a very valid form of attack, and it actually did work. And the best part about it from a hacker's point of view is that the answer is cached for the TTL chosen by the attacker. Remember, the attacker is actually returning the entire DNS record. That includes the time to live value and how long something should be cached for. So it was very common to see very large TTL values in cache poisoning attacks. So how do we combat this? Well, the early mechanisms were, let's just ignore non-authoritative answers, right? So if you don't accept data from questions you didn't ask. And there's some chaining and stuff that has to be taken into account too. But generally, you shouldn't accept stuff that's below not authoritative for where you asked. And note that parents do have to supply glue addresses records for in-zone child name servers. I did talk about that in part 1. You should go watch that if you're interested more in about that subject. But resolvers should also check that the IP address and the UDP source port is correct and that the DNS ID field is correct. And senders should make it really hard for these to guess so that flooding takes, a whole lot of random attempts and not just being able to predict the next value that might be sent. So you should randomize your source port number and you should randomize the ID field in the DNS. And that gives you about 32 bits of randomness, but that's still not cryptographically strong. And it doesn't work for on-path attackers either that can see and copy the requests in the first place. So the real question is, can we fix it? And I hope I got at least that song stuck in a number of people's heads. Well, we can, and there's some data protection mechanisms. So there's 2 different types, really. There's object security of how do we actually validate an object versus path security, which is, how do you actually validate that the path you got it over was secure? And there are 2 different forms of protection. So object security is done by DNSSEC in the DNS, and it adds cryptographic signatures on all the records. It's signed at or near the data's origin, and then once it's been signed, it really doesn't matter how you get there. It's verifiable in the middle of all the transactions. It's verifiable at the end, but it only provides integrity protection. It does not provide any privacy detection. Those records are queried all over the DNS tree, and various parties can see it. Path security, on the other hand, which has become a very hot topic lately for DNS over TLS and DNS over HTTPS, for example, and possibly even DNS over QUIC at some point, tunnels the answers between 2 points, and it does this with both integrity protection and encryption. But it offers, point-to-point protection only, so it verifies who you got it from, but not actually what it is. So it's not able to verify that the data on the other end is actually correct. So what is going on here? Well, they have 2 very different complementary properties, object and path security. So which are you going to pick? You have to pick one or the other, right? No, you actually don't. Object and path security work very well together, and you'll find that many endpoints of path-based approaches, like public resolvers, are actually doing DNSSEC validation so that they can prove that the object they tried to validate was secure before tunneling it over to you. So there's nothing wrong with putting a locked box in a tunnel. So a brief recap of DNS security technologies that exist to date. The object security, like I've been talking about, is DNSSEC, and it is records that were assigned by the authoritative source or somewhere near it, and it's talked about in a number of RFCs, including 4033 is the most recent one that is at least a current standard. The path security, on the other hand, there's a number of options to pick from. There's DNS over TLS, there's DNS over DTLS, which is the UDP version of TLS. There's DNS over HTTPS. There's oblivious DNS over HTTPS, which is being talked about in the DNSOP working group sort of right now, and actually I think it might be in the security dispatch group this coming IETF, so you might consider attending to that if I got the schedule right. And then there is a DNS over DNS using shared keys. So TSIG is actually a very old protocol. There's a recent update to that document, hence the large RFC number, but it's actually one of the older ways to do secure DNS using shared keys. And DNS Curve was another technology that was proposed at one point, which is another point-to-point encryption and authentication mechanism using elliptic curve, and that's still used and deployed deployed in a few places around on the internet as well, but it's not standardized within the IETF. So the thing to note about all of this is that there are various areas of all of these transactions that need to be secured, right? So the path-based mechanisms like DO, DOT, and DODT, and any of the other ones authenticates and encrypts the user to the resolver's protocol traffic. It is on the left-hand side of that. DNSSEC, on the other hand, is really designed to prove that the right-hand data set has not been modified anywhere from the root all the way down to the answers you actually need. Now, can these protocols be used in the opposite? You know, can you do path security on the right? Yes, but it's not being done. Can you do DNSSEC on the left? Yes, it's not being done as much. There are some instances of DNSSEC occurring on the left-hand side, but not as much. It can be used in both places, but it typically isn't. So again, this is the reason that they pair really well. So the nice thing about DNSSEC is that it secures records no matter where they are, right? So if there was a record that was created in example.com and it propagates up to, you know, various DNS resolvers in ISPs or even in cloud infrastructure, and it could get all the way to your home router, and then possibly all the way even into your local infrastructure, especially if you're running mail servers, it's much more common to run something very local. And then it doesn't really matter, right? That locked box is verifiable no matter where it came from, including over a swallow, you know, carrying a coconut and possibly a locked box of DNS information as well, or the IETF RFC on communicating over avian carrier. So how does it work? The DNSSEC is a hierarchical signing mechanism where there's public-private key pairs created at various points along the tree. The resolver typically only has the one key, possibly a couple of keys to be their trust anchor of where that they accept stuff from that is signed. And they do this by checking all of the records from the chaining on down. So the root zone signs with its DNS key the DS record of COM. So a DS record is just a pointer to COM's key, which then also has a DS record for example.com and a signature on that. Note that this is a very high-level presentation, so there are many other things that we could talk about that I'm leaving out. But basically, by following this chain all the way down, a resolver is able to provably identify that records have never been tampered with since they were created by the original owner, regardless of whether it was example.com or com or the root, for example. And the nice thing about it is that all of the records within those zones are then protected if they're included. So you can put other records, like all the text records that Jeff just talked about, for example, are all equally as well validatable. So the resolver in the end, after it is said, hey, all of this is great, client, here you go, here's the answer, and I'm going to set the AD bit. AD is equal to 1 means that I checked it, it is secure, DNSSEC has validated the whole tree, you're good to go. Except that this message typically isn't sent securely. So remember that the resolver talking to the end system is typically not secure, which is why some path security actually makes a great thing to pair with object security. So going back to the high-level overview, object security provides end-to-end integrity protection. It works everywhere. It is a distributed trust model with minimal configuration. Typically, you only have one trust anchor, but it doesn't provide any privacy protection whatsoever, and it typically is not deployed all the way to the end user, which is typically referred to as the last mile problem. Path security, on the other hand, provides privacy protection and point-to-point integrity protection, which is fantastic, but it doesn't verify that the data actually came from the original origin. It only verifies that hop that you're communicating over. And for true security, it also requires that every link be protected and trusted, right? So if data is being transferred between 3 or 4 entities on the internet, you'd better be able to trust them all, and you're actually not the one typically querying them. So, but it does very much solve the last mile problem and solve some privacy issues as well. So path security and object security are really stronger when used together. Object security protects the data. Object security ties the data to its source. Path security, fixes that last mile problem all the way to the end user, and it provides encryption, protecting clients from on-paths eavesdropping. So we're going to switch a little bit now into other ways that the DNS has security issues and some solutions around them. because the DNS, is primarily a spoofable UDP protocol-based design in order to keep things low, although TCP is used as well. Most DNS responses are larger than their requests, and thus it's a great source of reflection attacks. So if the entire world is sending a whole bunch of resolvers, UDP packets that are spoofed, containing the source address of the victim, well, all of those responses are going to end up at the victim, unfortunately. And so this was a bigger problem back in the day, but it's still a problem today. And one of the reasons that it is, we'll get to actually the solution to that in a minute. Let me talk about the other side of the DDoS targets. So because nearly all internet communication actually starts with DNS lookups, it itself is often a DDoS target. And I'm sure many of you have seen some of the highlights in the past number of years, especially the Dyn outage a number of years ago that knocked out a good portion of major websites across the US because it was the target of a DDoS attack. So to battle, oh, I'm missing an L there. To battle aggressive clients, one thing that has been done a lot lately is deploying something called response rate limiting. And it really is saying, hey, client, you've asked a whole lot of the questions, in the past N minutes. And in fact, they've really all been the same question. I'm not going to answer you anymore. I'm going to punish you, and I'm going to give you only partial answers or no answers, but I'm going to set the truncation bit, which means that you should come back over TCP, please, or implement DNS cookies. Either one of those is a solution, and that proves that you have end-to-end communication, and so UDP spoofing no longer works. This helps prevent overwhelmed UDP spoofing requests and is very commonly deployed these days in multiple implementations of DNS authoritative servers. It's interestingly not standardized yet, so there's actually some variations in how it's actually deployed and configured, but it's very widely implemented and very widely deployed at this point. To battle DNS outages, you should optimize your caches, because there's been a number of recent research studies that have shown that if you are on a network and you don't want to be affected by DDoS attacks, there's a few things that you can do. One, latest RFC is been published called Serve Stale, that basically says if you fail to get an answer to a question that you've asked, it's okay to use an old one, at least for a while. So that's, helps protect your local infrastructure from outages. And then if you can also run a copy of the root zone on your local resolver, which is RFC 886, and I have a local root project at ISI that actually allows you to mirror and simply mirror a whole bunch of other zones as well. There's also NSEC aggressive caching. This is actually highly beneficial to prevent validating resolvers from asking questions that they know that there isn't an answer for. One thing I'm not getting into today about DNSSEC is how you can provably know that there isn't a name within a zone based on some of the additional records, the NSEC record that I'm not talking about today. But it reduces traffic loads to authoritative servers by quite a bit. Now, the one thing to note is I gave you a short overview about all of the potential security topics at a very high level. Each one of the topics that I covered, including DOE, including DNSSEC, including path security and everything, could take an entire 30-minute segment on its own to dive deeply into it. So we didn't go into everything that's related to DNS security, but these are potential topics for future talks if people want to hear about them, or you can look them up on the internet for other sources of people that have talked about them. But for just to pick a couple of example ones, you can have multiple sources of trust anchors, for example. So I talked about the root of the DNSSEC key having its the DNSSEC having it, a single trust anchor at the root, but there are enterprises that actually also have a trust anchor for their local enterprise. NSEC3 is a slightly more privacy protecting on the zone owner side of way to prove that something doesn't exist. There's many ways of doing bootstrap security. That's becoming more and more popular, like DANE, PGP keys, SSH fingerprints, and things like that. All of a sudden become much, much more secure when you're actually signing them with DNSSEC. I didn't talk about how DNSSEC, you can actually know when you're falling into an insecure zone, for example. So DNSSEC actually does a great job of letting you know that you are in the secure portion of the DNS versus the insecure portion of the DNS. Anyway, there's a bunch of other topics. I'm not going to talk about them. I talked a little bit about QNAME minimization last time. There's algorithm strengths and rollovers, which are actually really being talked about right now. How do you deal with cryptographic changeovers when algorithms get weak? Jeff talked about query loops earlier. Then there's even unauthoritative servers, servers that answer for incorrectly. DNSSEC helps fix that at least. And then one of the biggest ones out there is, I'm sure you've all been in a hotel or been in a coffee shop that you have DNS intercepting middle boxes that refuse to give you the answers you want because maybe you're behind a paywall or something like that. And what sort of things, there's actually RFCs about that, as well as DNSSEC can help in that case. And there's a bunch of other things related to DNSSEC in particular about white lies and black lies, which I won't go into, as well as minimal signing. And there's many new things in working group states that are not included in these slides yet, except for a couple like oblivious DNS over HTTPS that are still being worked on. So with that, I'm going to turn it over to Joao, who is going to talk about myths in the DNS and some wonderful misconceptions and give you new answers. Right, Joao?
I'll try. Thanks, Wes. Let me start by seeing if I can share the screen. Can you all hear me, by the way?
Yep.
Okay, good. And all that's left is selecting the slides. Okay, so this last half hour, so is a collection of loose ends, but that people come up with frequently. So we decided maybe it's a good idea to do a quick review of common misconceptions about the DNS, so things people think work one way but actually work a different way. So let's go. Also, as I see that a lot of the people actually watching these live are DNS experts, feel free to add a compliment or correct at the end in case I got something wrong. So one of the usual things you see even at the IETF is that when people want to have a solution for a problem of disseminating information in a way, oh, that's helpful, Siri, that is accessible to everyone on the internet, and is propagating in a distributed way, it's often the case that they look to the DNS as the solution to all their problems. DNS, after all, is a success story, and so it also carries with it the burden of that success. One of the problems that people have in implementing that solution, I mean, after all, the DNS is there to be used, so everyone is welcome to use it to their best advantage. However, it should be realized that there are better ways and worse ways of doing this. One of the ones that has traditionally been abused, as Jeff mentioned briefly earlier, is the abuse of the text record. And I realized that there is an RFC from 1993, RFC 1464, that actually defines how you should dump stuff on the text record if you want to do that to solve your more immediate problems. It's still a bad idea. And the problem is the DNS defines not only resource records, but also the idea of resource record sets. And those are all the records of the same type that are present at a given name. And the DNS also defines those to be indivisible. So if you ask for a text record at a given name, the DNS server is obliged to give you all of them, even if you don't want it. So if you are the first one that uses a given text record to solve your problem, you're probably okay with it. But other people will see that and will try to use the same. And then after a little while, you won't be the only one using that. And then the problem comes. And to illustrate these, I'm just using this example that's now on screen, not to pick on Google or anything like that. But that is actually the result of a DNS query. You can do it live now, and you will see. And as you can see, there are 5 text records and 4 different usages for that. If you query for the text records at that name, you necessarily get all of them. And then you have to start parsing the ones that you want and the ones that you don't want to select and proceed. And as you see, there are the most diverse uses being made of these records. So, okay, so if that's not the best way, what is the best way? Well, the current thinking is that you should just get an RR type. The RR type code space is big. We are not filling it up at any rate that will put in danger the exhaustion of that space. So just go ahead and try to get one. It is not hard. There has been a myth that it is going to be hard because this would mean you have to write an RFC, go through the motion of the working group, back and forth comments and so on, and it takes very long time, and then it has to be implemented. Well, actually, no. There is a fast path to get a new RR type. You all you have to do is basically, as long as you don't demand that the name servers, the DNS servers that are delivering the information have to do special processing, they just do a standard lookup in a database to fetch a value for a key. So you just have to define what the format of that record is in a clear spec, in an internet draft, and then you submit it to a panel of experts. There's a standing panel waiting for you to send in the requests, your requests, and they'll review it and come back to you with comments or approval in a fairly short amount of time. So that's definitely the best way of getting things done for your application. Sometimes people also get confused about separating the namespaces, and one way of doing that would be, for instance, inventing your own top-level domain or buying it. Either of those options is not good. They are hard, they are expensive, they are pointless, and they cause more problem than it's worth. Well, I've jumped ahead of myself, I will say that. So don't get LDLD. If you get a proper internet one, you have to go through the whole ICANN process, and it's expensive, it's very hard, it involves layers. It takes a long time, longer than you might even imagine it was possible. And it's probably also not the solution to your problem, so not a good idea. If you make up your own TLD, which people have been known to do in the past, then the problems are of the sort. You don't have the approval process to take care of, but most likely down the road, at some point, you'll have clashes in namespace. Because if you mix your own newly created namespace with the internet's shared namespace, at some point, things are going to get hairy. There will be clashes. There will be indefinition of which namespace you have to address to get the information you want. And it's generally not a good idea. A network is only good as its cohesion, as the participation of everyone. If you split the naming space of the internet, you're actually splitting the internet, and then you have, instead of one big network, you have two smaller networks. And each of them has less value. Now, Jeff alluded to this, and whether names are for humans or not, what is the purpose of names? Well, in the beginning, everyone was kind of happy with ASCII, with just identifying machines and so on. As Jeff described, things got more complicated with time. And obviously, one of the things that humans want is to speak their own language and write in their own language. And that wasn't possible in the DNS. There were attempts at trying to define DNS labels that would be able to encode Unicode characters, but it didn't quite work out. Actually, in fact, the problem is not with the DNS itself. The DNS itself would be happy with any sort of stream of 8-bit values that it was given. But the implementations and the applications that make use of DNS started interpreting things in a way that implied the use of ASCII. Soon after the usage, for instance, it was implied that capitalization of a name should not be taken into account for comparisons, and that you should only expect a certain number of characters. And that kind of, even though the protocol itself allowed for 8-bit clean labels, in the practice, all the implementations and applications that made use of it stopped that being a possibility. So we still wanted to write in our own languages, and the IETF came up with the idea of IDN, Internationalized Domain Names. And what this does is define a way of encoding Unicode characters for many scripts in a DNS-compatible ASCII representation. It does work, but while it solves the problem, it creates new ones, as is often the case with many things humans do. One of the problems is that several characters in different scripts actually look the same to the human eye when they are represented by a web browser on screen, for instance, or any other application that makes a visual representation. Some of them don't look the same, but are remarkably close to each other. And for instance, I'm putting the case there of the Latin I, which has a dot on it, and the Turkish I without the dot. I think the letter is actually called Ha, which you'd think is easy to spot. But if you have a long text, it's probably not that easy. So this creates problems because bad people are bound to be using these against good people, innocent people in the internet. So as an example of the representation, I'm putting these up there. There's 3 domain names, probably sound familiar to everyone. I dare you to click on any of them, see where you go. And that would illustrate the problem we are talking about. There's a website to generate the names with homoglyphs, characters that be on the screen to be something else, to see the same as the ones you want to represent, but actually represented differently. And this is a sort of problem which relates to OS problems on security. So again, what are the valid characters on the DNS? Well, the DNS itself, as I said, doesn't actually place a restriction on what characters can be used. The only restriction that DNS places on names is about size. Each label can have up to 63 bytes, and altogether, a name made of several labels can have up to 355 bytes. It's almost like they wrote this in Pascal. But applications do place restrictions. Some of them are applications or common uses that were already inherited by the DNS because they were in existence before the DNS came into place. And one of those was the hostname restriction that Jeff also mentioned. Also, the restrictions or conventions have been evolved with the time. Soon after the DNS was defined and the concept of a hostname was defined with some restrictions, it was altered. Because in the beginning, you weren't allowed to have domain names that started with, or domain labels that were started with a number. And there used to be this famous company called 3Com that had a problem with that. So we changed the rules. Still, for instance, today, and this illustrates the principle that you should be liberal with what it said, things like 411.org exist and work, even though the standards say that a label should have at least 1 letter, something that is not a number. You should not be able to have labels that are only numbers. But there you go. They exist and they work. So how do we represent these IDNs? As I mentioned, it's an ASCII-compatible representation. There's a encoding called Punycode. That's how we represent these names. You see an example there. At the left side, you see the representation that the DNS actually stores and delivers to the application. But on the right side is what the application represents. And you can find very interesting examples. For instance, in that example, dots, several dots, .example.com. It's not clear to anyone just by looking at it where the actual dot is, where the label begins, where the label ends, and that poses problems. And it's kind of a hard problem to solve, to be honest. So a lot of these problems come from the fact that people are more and more thinking about the DNS as if it was a search engine, and by God, it is not a search engine. If you want a search engine, go to Google, Bing, whatever you like, your preference might be. But the DNS is not that. So just an aside. Okay, another thing people often stumble upon in the DNS when they use the DNS is an asterisk a valid label, or is it something else? Well, it is a valid label, but its meaning depends on where it appears and how it appears. If it's used in a query, it might be a wildcard, not exactly a traditional label. However, it's only a wildcard if it appears by itself. It's the only character in that label, and it's the leftmost label. In any other place or combination, it stops being a wildcard. So don't think about Perl regular expressions. That's not what this is about. It's just a one instance of a wildcard, and it only works as such when it appears in the circumstances. You cannot combine a star to mean all the names beginning with A. If it is stored in a zone, it can be just the character asterisk, just like if it appears anywhere else in the query. And asterisk, as again, is a valid name in the domain name because the DNS doesn't place the restrictions in the names it can store. So you might as well end up with a name that's just an asterisk. There's also a distinction that people fall for in this when using DNS wildcards, because often you use the DNS to lead to websites, and websites are executed with certificates that allow wildcards. A leftmost label in DNS can match any number of labels down deep into the tree to its left, but the certificate as to be used, an X509 certificate to be used on a website only allows one level of depth, which is a good thing, but you have to keep in mind that difference. You cannot just expect to get a wildcard certificate for all the names in a tree and a subtree under a given name. It's just limited to one level. So to illustrate how the DNS wildcards exist, I've created an example zone under example.com with those 4 text records. And there's a bunch of queries that are issued towards that name. And it will be the exercise for the reader to figure out what is the response that you'd get. So here's the solution, just to abbreviate. The first one, of course, matches exactly. The second one, see as example, as you see, doesn't exist in there's no label, that name doesn't exist in the zone above, so it gets matched by the wildcard, the first record in the zone. So does asking for the wildcard itself, you get the result back. However, if you ask for a.start.example.com, you don't no longer get the wildcard response, you get that exact match because it exists. And you can see that the wildcard is not the one matching, because if you turn A star to B star, which does not exist in the zone above and is not matched by the wildcard as defined before, you get an NX domain. So hopefully that clarifies wildcards a little bit. The subject was confusing enough for even the people who spend their lives in the DNS, that 20 years after the creation of the DNS, the definition of the DNS, someone, Ed Lewis, had to write an RFC to define what wildcards meant. So when you get no data from a response, from a query in a response, what does that mean? Well, it can mean several things. Depends on what the no data response coming back at you contains as information. It can have a given response code, hardcode 3, for instance, which means NX domain, which translates to that domain name you asked me about doesn't exist, nor does anything below it. It's the end of the tree. There's nothing here, or is there, nor does the tree continue in that direction. So try something else. There's a response type that people in the DNS call no data, which is actually a little bit ambiguous because it's not defined with that name anywhere. It's the combination of the fact that you get a response with rcode 0, which means there wasn't an error, and yet there is no data in the answer section. So if there is no error, how come I asked a question and I still got no data? What's going on here? Well, it can be both of two things. One is that you ask for a type of data that I don't have any information for. If you ask me for the IPv4 address for a name, but they only have an IPv6 address, for instance, well, I cannot have, I give you an answer with data, but that doesn't mean the name doesn't exist and there is any other type of information there. So you just be careful what you ask for. The second is what has been called an empty non-terminal. It might be the zone, presumably the zone example.com, that you have a.b.example.com as a valid record in that zone, but b.example.com doesn't exist. So if you ask for b.example.com, what you get is an empty, no error response, meaning that I know nothing about that name, but there's actually stuff that is a subdomain of this name in the same zone, by the way. And then there are other errors like serve fail and so on. This is a little bit of a further explanation of what an empty non-terminal, an ent, not in the Tolkien way, but in the DNS way is. You can refer to it back. I already explained it. So CNAMEs have already been mentioned, and why we always mention them, because they are a source of confusion. What the CNAME stands for is a canonical name. You ask for a name, and that response to that tells you that the name you ask for is actually this other name over there. And because you cannot be here and there at the same time, because what you are telling in a response is that I'm not the name you wanted, go look somewhere else, you cannot have then information of any other type associated to the name that's source of the CNAME, because that would immediately introduce two sources of truth into the system, and you won't be able to really know which one was the correct one. As a consequence of that, a zone's apex, which is where the start of authority for the name is, as well as the name servers for that zone are defined, cannot have a CNAME, because it would imply that there is more information at the same level as a CNAME, and that again creates trouble. It's not allowed by the current definition of the DNS. However, that doesn't prevent people from saying, and thanks to how liberal the internet is in what things it's willing to accept, some people actually abuse this mechanism and mostly get away with it. The IETF is now defining a proper way of dealing with this use case. So if this is a good, successful, worldwide distributed database, surely all the servers that are authoritative for a given set of data will have the same information. Well, yes and no. The DNS was never meant to be strictly coherent. It is actually what is defined as the loosely coherent. There is one source of truth, as in any decent database protocol, and that's called usually a master server or primary server, which is helped in its function by a set of secondary or slave servers. Slave is out of use now. We call them secondaries. That will reflect what the primary server tells them is the new information, but might take a little bit of time to catch up. So in that sense, there is a loose coherence, which will catch up. The system usually catches up with itself as time goes by. Short amount of time usually. There is, however, the fact that, as was mentioned earlier, there are recursive servers that cache information, and that information is cached for a given amount of time. If the source of the data changes that data in the meantime, that recursive server, that caching server, will contain stale data for the duration of the TTL. So that's one way where things can be a little bit off sync. It's again self-correcting with time. However, the latest fashion in the internet is that people play tricks with how to serve, what information is served. People will answer differently, even with different IP addresses for a given name, depending on where you are and how you reach them. Either by looking at your IP address and saying, okay, if your IP address, according to my local database, is from North America, so I will give you an address for you to connect to that's located in North America. Why is a user that is asking from Europe will probably get an IP address that points to a server in Europe. That's fancy using. It's transparent. Most people are okay with it these days because everyone chose to do it. But it can lead to interesting debugging problems. We chose to publish an informational IRC in how to make this a little better, which was an attempt called EDNS client subnet, which is some sort of signaling of where the client that's behind me is located, so that I'm asking in the client's behalf, give me information that's pertinent to the client. In exchange, you get told information about where the user is, and this can be exceedingly granular, so you might be exposing exactly who the user is. We have had in the last few years a couple of flag days in the DNS. They are mostly not really flag days as we people tend to think about flag days, but they are dates on when people agree that they'll change the behaviors in their implementations or on operations. In operations, it's nearly impossible to actually have a flag day that's effective. So it's mainly a communications tool these days. The DNS is implemented in millions, probably, of hosts around the world. And even if you only look at servers, it's unwise, unrealistic to expect that the whole deploy base would switch in a given day just because you ask them to. That's not how things work anymore. So it's more than anything a communication day to make people aware of changes that are desired and agreed to in the DNS, but they don't come into effect as a usual flag day would. A little bit of a myth is that CPEs, the routers, the things that you have at the edge of your home network, office network, enterprise network, work well as DNS resolvers. Well, misconceptions here are several. One of them, the most typical, is that CPEs are actually not running usually resolvers. They are running forwarders. What is a forwarder? Is something, piece of software that has a small little cache locally, trying to help you to get future answers quicker, but it actually just forwards your question to a proper recursive resolver that does all the heavy lifting on your behalf. So that's the first one. And then there have been ideas of or opinions or recommendations of whether it's good or bad to have a local recursive resolver in your CPE if you are allowed to, or if you are inclined to implement one. And there are both good things and bad things about these. I'll skip these because I'm going to run off the time, but the slide is there for reference. Another myth. If you turn on DNSSEC, everything in the DNS becomes too slow. Well, too slow for what and for whom? Which is always a qualification you have to make when you make a statement like that. So it is true that if you make any operation that you were not doing before, it will take additional time to do that operation. That's true here and anywhere else you do. But actually, the DNS has a feature that might reverse this in some cases. When DNSSEC was defined, it was decided that not only will it sign that a piece of information that exists will be attested to by a signature, it was also decided that the DNSSEC would have to prove that when a name does not exist, it can be proved cryptographically as well. And this was implementing by creating a gap record, the next secure NSEC record, which says in between two existing names, in this interval between two names that I know exist in the zone, there is nothing. So and you can sign that because now the absence of information has become information that exists, and it can be signed. Now, if you were to ask a name server for something that doesn't exist and it falls in one of these gaps that has been documented and proven to exist, you can use that previous answer as a way to shortcut the lookup and say, well, this domain doesn't exist either because it falls in the gap identified by this NSEC record, which I have proof of being true. So it can accelerate DNS lookups for the domains that do not exist. Also, because the lookups for names that do not exist actually take longer than any other lookup in the DNS, because the DNS will always try very hard to find the information you were asking about. So if you still experience problems with DNS slowness when DNSSEC is enabled, maybe your problem lies elsewhere. One of the things that happens when you carry more information in the DNS message, which DNSSEC always implies, is that sometimes those packets turn out to be very big. Sometimes they are so excessively big that they don't fit in a single UDP packet, and that packet becomes fragmented. Now, some networks take exception to the handling of fragmented UDP packets. And if they drop that and they don't have or don't enable the fallback mechanisms that the DNS has from the beginning, like use TCP, then you might have a big problem in your hands. But the problem is not necessarily with DNS, but rather with the network and the network management. Other things that may happen is that middle boxes, well, they are not always up to date or are not implemented by people that knew what they're doing at the time they did it. DNS, being while it is at the root of everything you usually do on the internet, it always seemed like the neglected child of all the protocols. You wanted to go to the website, you wanted to fetch a file, you wanted to send a mail, you wanted to know about the time. While DNS enables all those applications, it does so in the background, so most people are not aware of it. And it just also happens to be a very stable protocol and operation, so it kind of fades in the background and most people don't think about it, and then stuff happens. As I mentioned before, TCP and the DNS has been a thing since DNS began, since the origin of times. It's TCP in the DNS is always used for some of operations like zone transfers, because they involve massive amounts of information being transferred from one place to the other. But it should always be available as well for a standard fallback mechanism when UDP has issues. And we at APNIC have published several papers on how many people are affected in today's internet by issues like UDP non-handling, mishandling. Also, it can be that clients choose to use TCP right away without trying or attempting UDP as a first step that is allowed by the protocol. If you use TCP, when you use TCP, the only thing you have to keep in mind is that the protocol and the state that is kept in the servers that serve TCP is a little bit different than the usage of UDP, but the myth that this cannot be used is easily defeated by if you look at any standard big web farm that always uses TCP. So it's totally doable. You just need to be a pro. You just to care about what you're doing, your craft. And to end, we thought we would add a question here. There is a DNS query type that stands for any. Query type 255, also used in the old ones or broadcast kind of thing. The official name for it in the standard is star, and no one uses that name for it because we already have trouble enough with the other star, the wildcard one. We don't need to introduce any more confusion. So we call it any. Now, even so, since the beginning, any was defined as not to be all, but really anything you have about this name, or give me all you have about this name. This might not be all there is about that name in the DNS. For instance, if you ask a caching server that has some records regarding that name because it was asked about, I don't know, an A record, an X record relating to that name earlier on, and you ask it, give me anything you have, it will give you all that it has in its cache. It doesn't mean that it will give you everything that the authoritative server have on that. So you have to be careful, particularly because this is a debugging query, that if you know what you are debugging and that the information you are getting might be partial. And I think that is the last of the myths we wanted to address in this thing, because we had 30 minutes to go on it. And now it's time for questions, comments, insults, if you must. And I hope my co-chairs, co-speakers will still be around and able to join me.
Nope, you're around.
Let me just stop the sharing.
Thanks, Jeff. I think, I'm sorry, not Jeff. Thanks, Joe. I think, you know, the any all problem is definitely one of the myths that most people don't know.
Yeah.
If anybody attending the IETF crowd wants to ask questions or yell at us, please raise your hand and we will maybe that was all perfect and we have no questions. Does that actually happen?
That'll be a first. Did we put everyone to sleep?
Warren.
Oops. Go ahead, Warren.
Warren, so you mentioned that the any query causes a lot of confusion. I think there's been some talk about deprecating it. What do you think of that as an idea? Like, do you think it causes more harm than good, or not, or what?
Well, I like it. I use it when I need to debug, but I know what what I should be expecting from it. For the general public, perhaps it is misleading. So some people are already choosing to not implement it. It's one of the valid response codes that you can get from the DNS, and it's a valid choice. So by all means, go ahead and do it. You don't have to implement things you don't like to be DNS compliant. I wouldn't deprecate it. I think it still has the occasional useful purpose.
What might that purpose be, Joel? Because in some ways, you know, I fail to actually understand when any query does something that you couldn't do with other queries. Does the name exist? Well, you just need to ask even any other resource type, including text array, and you get no data. The name exists.
You can use it directly at the recursive server to find out if the recursive server is dropping certain records on the floor because it doesn't like them. If you know that the record is in a zone and you ask the recursive server for it, you get back no answer. You can try to trigger this and see whether where the name is disappearing in the resolution process. You can see if it only got partial information, which might be a pointer to a misconfiguration somewhere. It is useful. It's not a solve all thing, but it has its use cases. But it's a debugging tool. It's not something you should use as I'll shortcut my lookup time because I want to have both the IPv4 and the IPv6 addresses. So please give me any. That's not the way it's meant to use, and you might be surprised by the answers you get or not.
I know that there are reports of real queries that are happening, not just those that are trying to get all the data they can. That there's some applications. I think there was a mail server that was by defaulting querying for any, and in order to get back data about Amexes and stuff. So turning it entirely off is potentially unsafe.
Yeah.
All right, was there any? Robert, go ahead.
Can I come through? Are you hearing me?
Yep.
So, quick question. Do you think the DNS has aged gracefully over its, is it 20 years, you're saying?
It has a what, sorry?
Has it aged gracefully in terms of a protocol? Do you feel that it's still good for its purpose, or has it outgrown its initial roots?
So that has been so widely discussed, and when you get something as entrenched as the DNS, you know, the thought of doing DNS version 2 is the phrase that has been kicked around for 20 years as well. You know, should it ever be replaced and reconsidered with something new? You get huge issues with trying to you know, to update that much infrastructure. I think it is scaled amazingly well. I think that if we were going to redesign it today, you know, we would certainly change some things. There are, you know, one of the biggest desires that people have right now is, can I, and I talked about this last time, can we put more than one question in a packet? And you can't. And the issues around that are, you know, that the resolver would have to wait for multiple answers and try and figure out how to answer all the questions, and what happens when you get multiple errors, and all those types of problems exist, which is why you shouldn't put more than one question in a packet, even though there's a myth that you can. The reality is you can't, because no implementations support it for good reasons. That being said, I think if we were redesigning it today, the fact that so many things are being asked for, you know, Jeff talked about the HTTPS record, and we're talking about the A record and the quad A record, and I mean, how many different things can you query for that you actually want answers for all at once?
Well, I think it has reached quite well. I mean, it has been extended beyond what everyone imagined, with crutches given, but it's still fulfilling a lot of the purpose it was meant to fulfill. Defining an entirely new protocol to replace DNS is going to be extremely hard, because why would anyone put things in a protocol that is mostly void of information at the beginning? If I wanted to be provocative, I would say that actually we have sort of an opportunity to do a new DNS new generation, by abusing perhaps this thing called DOE, because it allows a lot of flexibility and extension there, while still retaining backwards compatibility if you want to. But that's a discussion to have amongst all of the IETF, I guess.
I disagree, and actually think that the cracks are showing, and they're pretty fundamental. The original specification of the DNS was as a predominant UDP protocol. So predominant was that the maximum payload size in a DNS packet was meant to be in UDP 512 bytes. And for simple, here's a domain name, give me an IP address, there was no reason conceivably that you ever needed to go more than 512 bytes. And large packets in the DNS were kind of odd and an exception. At the same time, let me remind you, the maximum packet that a v4 compliant host had to accept was a maximum of 576 octets. And a host was quite able to drop 577 octet incoming IP packets. So we designed the DNS to sort of sit within this small size, and large packets were the exception. The way you got a large DNS response through was you sent a small response with the truncate bit set, which was triggering the client to go to TCP, and you've just wasted 1 round trip time. And so these days, when we talk about DNSSEC, when we talk about service records, when we talk about large text records, and we sort of get the view that, you can put anything in the DNS, you can, but then you stress out the transport protocol problem. And the issue is that a whole lot of folk, particularly clients, lie like crazy in the DNS. Sure, I can handle 4096 octet UDP fragmented packet trains. Wrong. Send them one of those and it goes, huh, what happened? And so this whole area of the sort of mutated transport in the DNS, where UDP is prime, TCP is backup, has worked badly. Now, we then go, well, okay, let's just go all the way and use DOT, DNS over TLS, or DNS over HTTPS. And even if you think about it, DNS over HTTPS 3 or QUIC is just a mutated TCP. It's just taken up one level in the transport layer. But you have, in essence, the same sets of problems. Now, we point to the web and say, it is possible to create totally massive HTTP-based service infrastructure. And that's true. Totally true. But we built a massive UDP-based system where TCP is the exception. And there is an awful lot of money required to actually make the DNS work over TCP in all cases, because throughputs and servers, etc., don't actually work. Now, put that to one side, and then let's look at the DNS resolution economy. Who pays to get DNS answers provided? Well, it's not me. I'm just the user. And so when you say we have to forklift the entire DNS resolution infrastructure up to cope with TCP, because that's not where we started, you immediately open up this massive economic issue of, well, who's going to pay for that? I want my DNS to be free. That's what it is all about. No one pays to have names resolved at the query, the client side. So we're kind of between a rock and a hard place, that while UDP is difficult to make secure, it has enormous troubles with privacy. the effort to add encryption is largely a failure in UDP. And we kind of look at this and go, well, we really need to move on with that transport protocol. This whole UDP thing is a 1980s concept. But the whole problem is a here to there problem. And the DNS is kind of stuck in nostalgia because it's cheap, it's easy, and that's what we all do. And trying to get us into some, if you will, TCP-based flow control algorithm, whether it's quick or TCP, it's the same thing in terms of cost. That's what's causing us absolute heartache. And I'm not sure I see a clear resolution of that, but I do see a clear desire on the part of many applications to actually push a huge amount of rendezvous information into the DNS. It's fast. It can be made relatively secure, particularly with DNSSEC. You can trust it. And quite frankly, if we actually made the responses even bigger, and I'm referring to DNSSEC chaining, which I think is brilliant, you actually can make validation work in a single round trip time. This is fantastic, but you're carrying a large, carrier load of information sitting inside these sessions. Will the network handle it? Yeah, sure. This is tiny stuff. Will the DNS infrastructure handle it? Well, we built that for UDP. So we're trying to put 21st century payloads into 20th century infrastructure. And that's where we're kind of, the cracks are really showing, Robert. And I think the answers are as much economic as they are practical. We're just not quite sure how to get there.
Thank you very much. And also I should say thank you to all three of you for your talks. Very, very interesting. So thank you.
Thanks, Robert.
Thank you.
Certainly glad you enjoyed it. Anybody else want to ask a question?
There's a question in the chat window, Wes. It's actually, I think, Joel. QMail used any... Actually, it's more of an observation, really.
Yeah,
Yeah,
it's
that's actually the one that I was thinking of. Yeah, QMail used any. There's a question of how widely it's deployed. I know in the infrastructure I run, I certainly see any still pop around quite a bit, and it's unclear if it's a needed any or if it's a or an abuse of any, and it's very hard to tell. I believe Cloudflare's systems don't support any's. Weren't they one of the ones that return not implemented?
Yeah, replying not implemented here.
Well, this again was this issue about pushing the DNS into content distribution networks, and it was sort of seen as, why do I have to push the entire elephant, out to the front edge of all parts of my network when all you're asking for is a query relating to a toenail? I really don't want to push the rest of this craft onward and outward. I'll just push basically cache-based answers and just a fragment of the DNS. If everyone asks for A and quad A, that's all I'll serve at the edge. Oh, you asked for any. If I want to be quick, I'll just say, here's an answer. The name exists. The rest of the stuff is not immediately available to the front-end shim that answers DNS. It's back in some database that, quite frankly, I don't have the time to look up. And I can see that as the way we try and make the DNS go faster, because, the other pressure that's on the DNS is it's too slow. And no matter what we do, someone somewhere, I predict, will always say it's too slow. And it's almost the impossible target. But that's I think the other reason why any, which requires, if you're going to go instead of any, all, give me everything you know, the answer is, well, this might take a while, and we're just not patient enough.
So we need response times in negative milliseconds. Yes.
Yes. DNS over tachyons, I think, was where we're heading.
Predictive DNS. Just like when you type in the Google search bar, it comes back at you with what might be the question you wanted. Same idea applied.
What do the two of you think about pre-provisioning DNS over HTTPS, where you actually get server-side push then?
Well, I've been pushing for pushes, using DNSSEC signed data for forever, right? So the whole thing that I had the whole slide on, don't accept stuff from authoritative and authoritative name servers for which you didn't ask questions. That's moot in the case of DNSSEC. Right, you can actually return other data, and so there's been discussions of, should we start accepting stuff if that if you're talking to some name server that actually knows what you want, why not
However, in the
submit
apps,
extra data?
sure,
Yeah.
but in the absence of DNSSEC, this would be a queen to
Right.
the earlier cache poisoning attacks that you mentioned in your slides.
It only works if DNSSEC is enabled. So that's the only time you should, you know, if you get this gigantic response back, you know, ideally over TCP, and it contains an entire zone's data, right? Here's the resolver believes that it has the top 100 domains seen by this ISP for the past hour. I'm going to give it to you all so that you can be, oh, look, it's a negative millisecond answer. But it should be verifiable.
Yeah. On the other hand, things like DOE, as I mentioned, if you look at using DOE as a way to get to the DNS as an API, it might be possible to introduce versioning, and then the sky's the limit.
Robert, go ahead.
I had another question for you. It's probably for you, Wes. So you mentioned effectively the split in terms of security between securing the path to, is it the local resolver or local request resolver, versus securing using DNSSEC upwards for the records. You seem to suggest that you don't need to take DNSSEC all the way down to the end host. Is that a correct interpretation, or?
That is not a correct interpretation of my belief. That being said, there's a lot of people that don't think that your personal phone, laptop, whatever needs to do DNSSEC validation on it because your resolver is doing it. My personal belief, and I've both won and lost this battle in multiple places, is that if you are using the DNSSEC signed data to store critical data that you are bootstrapping security off of, right? And Dane is a good example of that. PGP keys are a good example of that. SSH fingerprints are a good example of that. I don't trust my resolver's AD bit equal to 1 in order to ensure that I am accepting that data and it's valid. So my belief is there's no reason why we can't do validation on individual devices. They're certainly fast enough these days. That's not a problem. And it allows you greater respect with respect to being able to bootstrap security-related data that is already encoded in the DNS.
Well, I do remember, and it's an ongoing debate about Dane. Why haven't we got PKIX keys sitting inside the DNS and getting rid of the twisted and potentially corrupted version of all of those CAs in the web PKI? And the response from the browser folk has been, you know, when I talked about time, it really is an issue. And that while Dane can feasibly do this, one of the issues, not all of them, but one of the issues is that down at the end client level, performing validation, you know, on your own takes an extended amount of time. I've got to basically query backwards up the chain and get back all of those DNS key and DS records. And so that's also this push that says, if you really want to do this, and Robert, you can experiment with this and add your own stub DNSSEC validator. And I think you should, because it's certainly a learning experience as to how long it can take in terms of elapsed time to actually perform this validation. And that's the issue, that while the resolver, which normally is handling a lot of queries, caches this stuff up, and the validated answers are stored in the cache, down at the end user client level, there's nowhere near that intensive activity level that loads the cache efficiently. You're not combining strengths from other players, you're back on your own again. And because of that, the time penalty is, well, I think for most users would agree, the time penalty is excessive. And various efforts have been made to try and get around that. And the most successful I've seen is DNSSEC chaining, where you push the burden of work back onto the zone publisher, who, as well as publishing, this is my RR records, this is the signature, they actually publish a combined record, a DNSSEC chain record, which is the answers to all the validation questions you ever were going to ask about me. And again, because it's DNSSEC, that's okay, because you don't have to believe it. You can use the answers to validate what's going on. Now, that means huge answers. That means pushing huge answers in TCP out into stubs. And while that link between recursives and authoritatives is relatively robust and handles large packets and TCP adequately, I wouldn't say well, but adequately, the real problem is out there in stubland, where the amount of cheap crap that people buy, you know, there's an awful lot, numbering in the billions. It's not even clear how easily TCP gets out there or fragmented UDP. So while it's really good to say clients in mobile phones should do validation, and we think we can do that, the implication is, wow, we need to push large DNS responses out to these things. Gee, that's an issue. So that's why this becomes a vexed problem, that a good DNSSEC system should go all the way to the edge. We really don't understand how logistically that can be done within the bounds of current infrastructure. So that's kind of the tough question.
Do remember one thing when it comes to validation and slowness. It's only slow the first time. If you have a 3,600 millisecond, 3,600 second, TTL, then you only have to do it once an hour. But let's ask Monica in the chat window actually asked a question, which is how prevalent is eDNS client subnet, and how my screensaver kicked on right then, and how privacy sensitive is it, and has the data protection crowd detected it already? So Jeff, do you actually have measurements, or one of you have measurements around?
This is a really difficult question, Monica, because the folk who could answer view that the data that they get is so sensitive, they're not going to answer your question. And it's kind of, the problem is acute. Certainly, as we've observed in the analysis around initiatives like Oblivious DNS, the combination of who you are and the name you're querying for is extraordinarily valuable. It exposes what people are doing, absolutely. And so in that respect, this is a problem. Because when you think about the DNS, the query never has the querier. The querier is the source IP address of the packet. So when I query for Potteroo.net, I go through a recursive resolver. The recursive resolver knows about me, but if it's not in the cache at that point, the recursive resolver goes to the authoritative. The authoritative has no idea Jeff is asking. All it knows is the recursive is asking on behalf of, I don't know. Now, eDNS 0 says, no, Jeff's asking. It's Jeff. And you go, oh, but we've obscured it. This is a /24 subnet. Well, unless when someone configures it to do a /32, oops, which happens. Or in the case of V6, what's the right subnet size to obscure me? It's an extraordinarily difficult problem. And as a data leak, it's humongously bad. On the other side, the issue of content distribution networks, we've seen already with the service record that realistically, folk don't want to spend the time customizing the response and steering you to the closest entry point in their CDN through the application. To cut the time and throw the problem to someone else, put it in the DNS to give the right answer. I need an idea of the end user's location. The problem is addresses the location and identity. And to say, I just wanted to know where you are. I didn't want to know who you are. Our IP address infrastructure says, no. Can't do that. As soon as you get to know that address, even at a prefix level, it's pretty clear who you are. And disambiguating that is nigh on impossible in the current IP address infrastructure. So, one person's problem is another person's nightmare, Monica. And yes, it's incredibly sensitive data. And if I could answer your question, that would mean we're treating that data badly. The fact that I can't answer it in a generic way, I can't give you data, is, I suppose, some slight reassurance that the folk who are privy inside that resolution path do not make a habit of publishing what they know. And that's about as good as it gets, I think, in today's world right now with this. I agree with the caveats on the RFC, and there were a lot. And the caveats, as I recall, basically said, we're going to publish this because interoperability is good. We're not publishing it because it's the best way of doing this. We don't know what the best way is, but we think this leaks like a sieve. And I agree with that analysis. It leaks like a sieve. There really should be a better way of doing this, but we don't know what it is. If you really want to go down this path, the other path is don't expose any information at all. Oblivious DNS hides that combination. No one, not even a recursive resolver, gets to know who's asking what because you deliberately obscure it. And so that's this tension that the application folk want to assume that the DNS tells all. It rats on everyone all of the time. Over on the other side, DNS and privacy, which is a big thing in today's world. The answer is we're ratting on no one, and we're making sure that no one, not even recursive resolvers, are privy to the profiling of what users do. And, you know, we get as much security as we're prepared to wait for and we're prepared to pay for. And as long as the assumption is the user is incredibly impatient and waits for nothing, security is sitting there going, oh my God, how do we do this yet still provide an incredibly fast sort of responsiveness and feel? And I don't understand how to resolve that tension.
A lot of, I think, what we've been talking about in the last 15 minutes has been the tension around three pillars, right? You have security with respect to integrity, you have security with respect to privacy, and you have speed of response. You cannot optimize for all three at once, and things like ECS and don't do validation because I need to show the web page faster is an indication that it matters more to get speed over those other two. And unfortunately, users don't have the ability to actually select what they prefer, and also users typically don't have the understanding to be able to select what they would prefer.
Although Wes, our efforts to empower users have always been in some ways thwarted by the fact that almost no one fiddles with the buttons. And increasingly, the application folk have become impatient with that and are now arming the application with presets. You only need to look at the Mozilla Firefox decisions about their use of DOE in certain markets to sort of sense this level of impatience, that saying users have a choice, they can go into settings and do XXXXX is kind of speaking to the 1 in 1,000 folk who might do that. If you really want to move the dial for everyone, the application folk, I think, have largely now got to the point of going, I'm not waiting. I'm going to arm the application with the necessary behavior patterns. Sure, you can revert, but the default settings are decisions the application's making. So increasingly these days, users don't get, if you will, a say in this because there's no expectation users will exercise that right. Applications, not platforms, but applications are now making these default choices. Welcome to the new world.
But that's just a reflection of normal user behavior. I mean, you only care about security when something bad happens to you. And in the meantime, large e-commerce platforms are showing have data that a few milliseconds of delay in any of the transactions causes a measurable loss of close in those transactions, right? So, I mean, you only shout for the police when you're bugged. In the meantime, you don't want them near you.
All right, well, it looks like we are now at the top of the hour. I don't know if Warren wants to come back in and close us out or not, but thank you for everybody that listened to us today. And if we spoke too quick or you missed something, it'll be on YouTube. I'm pretty positive. I know it's already been broadcast there, whether it's archived there in the same place, I'm not sure. But
No, thank you all too for coming. Hopefully it's been useful.
Thank you all.
Yep, thank you everyone. And yes, it will be archived and will be on YouTube. I believe that Greg will also post it on the IETF website or a link to it, so people can find it there. And thank you very much to all of the presenters. I know it was a huge amount of work getting organized, but I think people really enjoyed it.
Enjoy not Prague next week.
Sob. Thanks. Bye all.
One of my favorite places to go to in Norway.
Sob.
Bye all.